Hello, future engineers, subscribers, viewers, and students. Here is another video which is devoted to solutions to problems in plane and spherical trigonometry. Some problems here are supposedly topics in plane trigonometric 4, which is the application of the spherical trigonometry, particularly on terrestrial sphere. But I just want you to review especially law of sines and law of cosines for spherical trigonometry. For spherical trigonometry, there are two laws for cosines, for the sides and for the angles, which I explain later when I discuss the solution to the problem, to that particular problem. Also, some of the problems here are belonging to topics already discussed in the preceding videos. So I hope that you can follow the explanations and you will be guided to the solutions to the problems. Anyway, I'll explain them. So this is, as I said, devoted to purely solving problems in plane and spherical trigonometry. So we begin with problem 8 because in the last video we ended up to problem 7. If verse theta is equal to 0.363, then find theta. So I told you this is another trigonometric function. Then you should know the equivalent of this function, which is equal to 1 minus cosine of theta. So this is an easy problem if you just familiar with the equivalent of verse theta or verse sine theta. And this is equal to 1 minus cosine theta equals 0.363. Then 1 minus 0.363 is 0.637, then equals cosine theta. So cosine theta is 0.637. Therefore, theta is the inverse cosine of 0.637. So using your calculator, it is equal to 50.43 degrees. The next problem, problem 9. Solve the spherical triangle whose given parts are A 72 degrees 27 minutes, B side B 67 degrees 49 minutes, side A, then side B, then angle C is 90 degrees. So this is a right spherical triangle and we need a guide. Just remember two rules, sin cos op and sin tan ad rules. So I cannot memorize those formulas. I accept because I don't memorize formulas. I just remember the two rules, the sin cos op and the sin tan ad rule. So I'll draw the right spherical triangle first. And remember that the arrangement of the elements, 5 elements except angle C, which is 90 degrees here, would be in the same order, same direction, and except those elements opposite to the 90-degree angle, which are replaced by their complements. So beginning with B, next is A, then B, angle B, side C, and angle A are replaced by their complements in this Napier circle, complement of B, complement of side C, and complement of A. Then we take note the given information always involved. This is my suggestion that when you solve problems on spherical triangles, always involve the givens. So A and B are given. So because I want to involve these two unknowns always to make sure that the answers will be independent, not interrelated. Because if one is wrong and you use that for the next solution, then everything would be wrong. So I suggest that the two given elements should always be involved in the solution. So this part, sine, which is complement of C, opposite to this part would be A and B. So I use sin cos op rule, which is the sine of this part, this middle part, is equal to the product of cosines of opposite parts. That is, sine of complement of C is equal to cosine of A, cosine of B. Then from trigonometry, sine of complement of C or sine of 90 degrees minus C is cosine of C. So this is now equivalent to cosine C equals cosine A, cosine B. Substituting the values of A and B, so cosine C equals cosine of 72 degrees 27 times cosine of 61 degrees 49. So with your calculator there, evaluate inverse cosine of the product of these cosines. So side C is equal to 81 degrees 49 minutes. Also expressed in the same format as the given sides or angles. Then after C, we may solve for angle A by setting up sin tan ad rule. Sine of B is equal to tangent A, tangent of complement of A. Or these three adjacent elements, sine of A equals tangent of B, tangent of complement of B. So I use sine of B equals sine of side A, sine of B is equal to sin tan ad rule, tangent of A, tangent of complement of A. Tangent of complement of A is cotangent of A, and cotangent of A is 1 over tangent A. Take note. So simplifying, sine B equals tangent of side A, which is tangent of 72 degrees 27 minutes, then cotangent of A. Take note that cotangent A is 1 over tangent A. So tangent A, if it is in the denominator, tangent A, is equal to tangent 72 degrees 27 minutes divided by sine of 61 degrees 49 minutes. So using your calculator, tangent angle A therefore is inverse tangent of the quantity tangent 72 degrees 27 minutes all over sine of 61 degrees 49 minutes. And angle A is equal to, so I still simplify it so that you can follow. So now you can use your calculator. A is equal to 74 degrees 25 minutes. Then lastly, to solve for angle B, because I want to involve A and B always, the givens, then I use sine of side A is equal to tangent of B, tangent of complement of B. So sine of A equals tangent of B, tangent of complement of B. So this is simplified into, because this is cotangent of B, and cotangent of B is 1 over tangent of B. So therefore, after cross multiplication, tangent of angle B is equal to tangent of side B over sine of side A. So tangent of angle B equals tangent of side B over sine of A. So substituting, tangent of angle B equals tangent of side B, which is 61 degrees 49 minutes over sine of side A 72 degrees 27 minutes. So inverse tangent of this ratio, we can compute angle B, which is equal to 62 degrees 56 minutes. So that's it for this problem 9. We proceed to problem 10. Solve for the spherical triangle whose given parts are angles A is equal to angle B, 64 degrees 34 minutes, and side B is 81 degrees 14 minutes. This is an isosceles spherical triangle because the two angles are equal, therefore opposite to these angles would be equal sides. So side A and side B should also be 81 degrees 14 minutes. And remember the property of an isosceles triangle or isosceles spherical triangle. If we drop a curve, an arc, great circle arc perpendicular to the opposite side, then we will divide the isosceles spherical triangle into two right spherical triangles as shown. So this is the spherical isosceles spherical triangles. Side A opposite to angle A is equal to side B opposite to angle B. So A equals B. Take note of that. So A is also 81 degrees 14 minutes, but we will solve that last. Then this is the angle that will divide angle C, and I will call this vertex as also C prime. This is B prime, this is C prime. So I'll call this A prime, which is 90 degrees, then B prime, and C, side C prime. By the way, side C of the original isosceles spherical triangle is double this value here. Remember the property of an isosceles triangle. So C is 2 times C prime after we solve for C prime. Then this angle here is also half of angle C. So I'll first mark it by C prime, and the measure of angles here is C prime. The measure of angle C is double that angle C prime. So let's focus on this right spherical triangle. In this case, the 90-degree angle is A prime, and therefore beginning with C prime, side C prime in counterclockwise direction, so the next element would be B prime. Opposite to angle A prime would be C prime A, which is equal to B, and angle B. So that's why we replace them by their complement. So beginning with C prime, next is B prime, next is complement of C prime, next is complement of A or complement of B, then lastly complement of angle B. Then we apply the rules. Let's check the givens, angles A and B. So this is given, and side A. So this is also given, although it is B here, but A is, remember, also equal to B. So if we want to solve for, we don't need B prime here because it's not part of the original isosceles triangle, spherical triangle. We only need C prime and angle C prime. So these three are adjacent, or if we want to solve for C prime first, then sine of complement of angle B is equal to tangent of complement of A, tangent of C prime. So sine of complement of A, so let's solve for angle C prime first. So it is equal to tangent of complement of B times tangent of complement of C prime. Then this is cosine of A, this is cotangent of B, and this is cotangent of C prime. So cosine of side A equals cotangent of angle B, cotangent of angle C prime. And remember that cotangent is 1 over tangent. So cosine of 81 degrees A, 81 degrees 14 minutes is equal to 1 over tangent of 64 degrees 38 minutes, which is B, times 1 all over tangent of 64 degrees 38 minutes, then times tangent of C prime in the denominator. So therefore, tangent of C prime is 1 over cosine 81 degrees 14 minutes times 1 over quantity cosine of 81 degrees 14 minutes tangent of 64 degrees 38 minutes. So using your calculator, C prime can now be solved and it is equal to 72 degrees 11 minutes. Since as expected, C is 2 times C prime, so angle C is 2 times quantity 72 degrees 11 minutes. So that would be 144 degrees 22 minutes. Then we solve by computing C prime next, our next objective. So take note that these two elements are given. So to involve C prime, considering these two givens here, so sine of complement, let's use in tan add rule again. Sine of complement of B is equal to tangent of complement of A tangent of Z prime. So sine of complement of angle B equals tangent of complement of A tangent of C prime. This is cosine of angle B. This is cotangent of side A, then times tangent of C prime. So take note that cotangent of A is also 1 over tangent, but it's, you just use your calculator. So cosine of 64 degrees 38 minutes equals cotangent of 81 degrees 14 minutes tangent of C prime. So to solve for tangent of C prime, it is inverse tangent because this is 1 over tangent 81 degrees 14 minutes. So it is inverse tangent of cosine 64 degrees 38 minutes times tangent of 81 degrees 14 minutes. Then C prime can now be solved. It is equal to 70 degrees 12 minutes. And since C is 2 times C prime, so the value of C is 2 times 70 degrees 12 minutes, and therefore it is 140 degrees 24 minutes. So the other element, which is A, is equal to B, because this is an isosceles spherical triangle. It is 81 degrees 14 minutes as is shown here. So problem 11 is supposedly an application of the terrestrial sphere in spherical trigonometry. So the concept here is explained in plane and spherical trigonometry 4, which will be in the future, to be uploaded in the future. But I will just give you mention the law of sines for spherical triangles and the laws of cosines. There are two parts. So in this problem, a plane flies from Davao with 121 degrees longitude, 13 degrees north as latitude, in the direction south 30 degrees west at the rate of 600 nautical miles per hour. If the radius of the Earth is 3,959 miles, when will the plane cross the equator? What is the longitude of the point of the equator where the plane crosses? So other facts and information about spherical trigonometry, particularly on terrestrial sphere, which is the same as the radius of the Earth, 3,959 miles, and 1 mile is 5,280 feet. The longitude, which is either east or west with maximum value of 180 degrees, is the angular distance of the meridian. The meridian is a great circle through the north and south poles of the terrestrial sphere. So 121 degrees east, so it is east of the prime meridian. The prime meridian is a great circle passing through Greenwich, England. Then the latitude is either north or south with a maximum value of 90 degrees. That's the distance of the place or point above or below the equator. And the equator is also a great circle. Now, if it is north, so that point or place is above the equator. If it is south, then it is below the equator. Then the plane travels in the direction south 30 degrees west at the rate of 600 nautical miles per hour. If the radius of the Earth is 3959 miles, when will the plane cross the equator? What is the longitude of the point of the equator where the plane crosses? So we need to compute the distance traveled by the plane along the side of the spherical triangle here, which is a right spherical triangle. But first of all, let's draw the sphere. And this is the equator. Then let us say this is the prime meridian. Because the longitude of Davao is 121 degrees east, so it is somewhere here. As shown, then this angle is 121 degrees, so that's east, and 13 degrees north, so Davao should be somewhere here. That's the angle subtended by this arc on this meridian at the center of the Earth, which is also this angular distance, which is 13 degrees. So that's 13 degrees. This is also 13 degrees. And this is the direction of the plane, the red side of the great circle, and it crosses the equator. This angle is 30 degrees. So angle D, capital D, is 30 degrees. And let's call this point E on the equator, the cross-section of the equator. And let's call this point M, the meridian means. Then the angle between this meridian and the equator is of course 90 degrees. So this is a right spherical triangle. We need to find the length of this side of the right spherical triangle, which is a great circle. Then by the rules, Napier's rules, there are two rules, the applicable rules here. And then we need to find the distance from D to E. So this is now the specifics of this triangle here. I'll call the distance from the meridian to E, from M to E by D. Opposite to capital M is small m. Opposite to E is small e. To angle E is small e, 13 degrees. And angle D is 30 degrees. So given would be angle D and E. Then let's have the Napier circle. So beginning with D here, next is E, then the rest would be complements of angles, complements of elements opposite to the 90-degree angle, which is capital M. So this is D, E, complement of D, complement of side M, and complement of E. So in order to compute the time it will take the plane to cross the equator, we need to compute this distance M here, side M. And since involved elements are angle D and E, side E, and M is next to angle D, these three are adjacent to each other, so I use Sintan-Ad rule. Sine of complement of D equals tangent of E, tangent of complement of M. So sine of complement of D equals tangent of complement of M, tangent of E, or vice versa. So simplifying, this is cosine of angle D is equal to cotangent of M, then tangent of E. Then so next is we simplify this into, because tangent of or cotangent of M is 1 over tangent of M. So cosine of D, which is cosine 30 degrees, equals tangent of E, which is tangent 13 degrees, over tangent of M. So solving for M, inverse tangent of quantity tangent 13 degrees over cosine 30 degrees. So M would be equal to 14 degrees 56 minutes. In plane trigonometry, plane and spherical trigonometry 4, the definition of 1 nautical mile is it is an arc distance on the surface of the Earth, the terrestrial sphere, subtending 1 nautical mile, subtending 1 minute angle at the center, just like this. So therefore, we need to convert this to minutes first, and take note that 1 minute arc distance is equal to 1 nautical mile. So M is 14 degrees times 60 minutes per degree, 1 degree, plus 56 minutes. So side M would be 896 minutes, so times 1 nautical mile per 1 minute. Therefore, it is also 896 nautical miles. So distance equals speed times time, so time equals distance over speed. The distance is 896, the speed is 600 nautical miles per hour, so we can solve for the time in hours. So time equals distance over speed, so time equals 1.493 hours. Then to solve for the longitude where the plane crosses the equator, which is at E, so we draw a meridian through E, and we need to solve this distance D here. This side D, because this is a great circle, is also the measure of that angle there. Therefore, the longitude of point E, where the plane crosses the equator, is 121 degrees minus this side D here, which is also east. So 121 degrees minus D. To solve for D, involving these three given, so sine of E equals tangent of side D, tangent of complement of D. Simplifying, sine of E equals tangent of D. This is cotangent of angle D, so that's 1 over tangent of angle D. So sine of E equals tangent of side D over tangent of angle D. Then we can solve D, inverse tangent of sine E, tangent of D. So sine of 13 degrees equals tangent of D over tangent of 30 degrees. So we can now solve D as inverse tangent of the product of these two. Inverse tangent of quantity sine 13 degrees times tangent 30 degrees. So it is equal to 7 degrees 24 minutes. Therefore, the longitude of E, this is the point where the plane crosses the equator, is 121, quantity 121 degrees minus 7 degrees 24 minutes, and that is east, 113 degrees 36 minutes east. We then proceed to problem 14. A point inside an equilateral triangle is at distances 4 meters, 5 meters, and 6 meters from the vertices. Find the side of the equilateral triangle. You might wonder why I jumped to problem 14, where are problems 12 and problems 12 and 13. Problems 12 and 13 are problems which are related to the preceding topics in plane trigonometry, plane and spherical trigonometry 1 and 2. So I do not involve them here because the problems are designed for those preceding lecture videos. So we'll just solve this problem, although this is supposedly part of the preceding problem, but this is a problem that needs attention, that you need experience on how to solve these problems. So let's do the figure. This should be the point, so that it is 4 meters, 5 meters, and 6 meters from the vertices of an equilateral triangle. So the technique in solving this problem is, if we call this angle between the 6-meter side and the side of the equilateral triangle as theta. By the way, we draw another equilateral triangle forming this longest side. So 6, 6, 6. Remember that the interior angles of an equilateral triangle are each 60 degrees. So this is another equilateral triangle. And if I call that theta, this is 60 degrees minus theta. And since this is an equilateral triangle, this must also be theta, because the angle here is 60 degrees and this must be theta, so that is true 60 degrees minus theta also. Or 60 degrees minus theta plus theta equals 60 degrees. So this is 60 degrees, that's also 60 degrees. And take note that in this triangle here, this triangle, adjacent sides to theta are 6 and x, which is the same for this angle here. The adjacent sides are 6 and x. Since in this triangle, opposite to theta is 5, we conclude without doubt that this missing side, or this side here, which I'm going to extend or draw, should also be 5. So because this is also 5, we can compute this angle by the law of cosines, then add it by 60 degrees. So we can compute this entire angle here and apply law of cosines in this triangle with the opposite side to that angles there as the unknown x. So that's the procedure in solving this problem. So first, let's solve for this angle. I'll call that angle alpha. So by cosine law, 5 square, opposite to alpha, 5 square equals, so that's 60 degrees, remember? So 5 square equals 4 square plus 6 square minus 2 times 4 times 6 cosine of alpha. That's the law of cosines. Opposite to the angle, square equals the sum of squares of the other two sides minus twice the product of the other two sides times cosine of the angle opposite to this side here. So solving for alpha with your calculator, alpha is 55.771 degrees. Finally, apply cosine law again in this triangle here. So x square equals 4 square plus 6 square minus 2 times 4 times 6 cosine of quantity 55.771 degrees plus 60 degrees. So with your calculator there, we can now solve for x, and x is 8.536 meters. Problem 16. Find the distance in kilometers between Annapolis, Maryland of latitude 39 degrees north, longitude 76 degrees west, and Cape Town, South Africa with latitude 34 degrees south, longitude 18 degrees east. So again, this is a spherical triangle, particularly because these places are points on the Earth, and the Earth is converted into the terrestrial sphere. So we have laws of sines and cosines here, which I'll explain later by solving for one of the sides of the spherical triangle that can be formed. So let's draw this and the equator. The prime meridian should be somewhere here at the middle, so that Annapolis, Maryland, I'll just call this point A. Let's draw a meridian through Annapolis. The longitude is 76 degrees west, so it is here, and 39 degrees north above the equator as shown. So that's the North Pole. So Annapolis should be there, and this is 76 degrees, and above the equator is A. That's 39 degrees because it's north. Likewise, Cape Town, South Africa, I'll just call it point C. The longitude is 18 degrees east, so from the prime meridian eastward, so this is the meridian through Cape Town, South Africa. So that's 18 degrees there, and that is Cape Town, 18 degrees, and this is 34 degrees because it's south. Therefore, the point A would be 90 degrees minus 39 degrees, so that's 51 degrees. So this side here, this meridian, length of this meridian is 51 degrees, 90 minus 39 degrees, so that we can find this distance and we can form this spherical triangle NAC, and we want to find the distance of AC. Likewise, this distance is north to equator is 90 degrees plus 34 degrees, so 124 degrees. So this is the distance, the red great circle distance. We want to find that. Then I'll call that N because it is opposite the capital N, the North Pole. So this distance is 124 degrees. Then 76 degrees plus 18 degrees is angle N, that's 94 degrees as shown. So I will apply law of cosines for the sides here because the sides are given and the opposite angle given. There are two laws of cosines, namely law of cosines for the sides and law of cosines for the angles. So that you will have an idea about the law of cosines for the sides, it is cosine of n, this side here, is equal to cosine of the other sides, cosine of C, cosine of A, or cosine of A, cosine of C, plus sine of A, sine of C, cosine of angle N, capital N. So that's the one of the three formulas for law of cosine for the sides. For law of cosines for the angles, cosine of angle N is equal to the negative of cosine of angle A, cosine of angle C, plus sine of angle A, sine of angle C, times cosine of side N. But we cannot use that because it is side N that is unknown. So I write the formula applicable to this problem. Cosine of side N is equal to cosine of side A, cosine of side C, plus sine of A, sine of side C, cosine of angle N, opposite to this side. So this is just one formula of the three. You can pattern the rest. So everything in the right side is given except the left side. So substitute cosine of n equals cosine of A, which is 124 degrees, cosine of C, which is 51 degrees, plus sine of 124, sine of 51 degrees, cosine of 94 degrees. So using your calculator, n is equal to 113 degrees 23 minutes. Then next we convert this to minutes. 113 degrees times 60 minutes per 1 degree plus 23 minutes, so that we can express that in minutes. Then remember, 1 minute is 1 nautical mile. So 6,803 minutes, which is also 6,803 nautical miles for terrestrial sphere such as the Earth. Then we convert this to kilometers. So n equals 6,803 nautical miles times 6,080 feet per nautical mile times 0.3048 meter per foot, or if you are not familiar with that, 1 meter in the numerator, 3.281 feet in the denominator. But 1 meter is 3.281 feet. Or 1 over 3.281 is 0.3048. So 0.3048 meter per foot. And times 1 kilometer per 1,000 meters. So the units now is in kilometers using your calculator there. N is 12,607 kilometers. Then finally, this is a problem in plane trigonometry. A triangle has sides AB 24 meters, BC 30 meters, and CA 28 meters. Find the distance from A to the orthocenter. So to find the distance from A to the orthocenter, remember orthocenter is the point of intersection of the altitudes. So this is the triangle. AB is side C actually, which is 24. BC, which is side A, opposite to angle A, is 30. And CA, which is side B, is 28 meters. And we are looking for the distance from A to the orthocenter. This is the orthocenter. I will mark this with point O. And the distance AO is I'll mark that with X. So we apply law of cosines to solve for angle B. You may solve angle A if you want, but in this problem, my plan is to solve for angle B so that I can solve HA. This is altitude through A, so I'll call that HA. Then later, this is H sub C. We can solve H sub C after we solve for angle B because it involves right triangles. So by cosine law to solve for B, so 28 square equals 30 square plus 24 square minus 2 times 30 times 24 cosine of angle B. So using your calculator there, angle B is equal to 61.278 degrees. So that means if this is 61.278 degrees, we can now solve for HA, which is equal to C sine of angle B, because HA is opposite to angle B and this is a right triangle. So HA is 24 sine of 61.278 degrees. Having found HA, which is equal to 21.047 meters, then we can compute this angle here. We need this angle here, alpha, and cosine of alpha is HA over 24. So I'll call this side also as Y. So cosine of alpha, which is equal to adjacent of alpha in this right triangle, HA 21.047 over hypotenuse 24. So alpha is equal to 28.722 degrees. Having found alpha, we then solve for H sub C so that we can solve for Y. And finally, from the figure, X cosine of alpha equals Y, or cosine of alpha equals Y over X. So that's the plan. So we first solve for H sub C, and H sub C in this right triangle is equal to 30, the hypotenuse sine of angle B, because H sub C is also opposite to angle B. So H sub C is equal to 30 sine of angle B, 61.278 degrees. So H sub C is 26.309 meters. Then, in this right triangle here, we can solve for Y by Pythagoras theorem. The hypotenuse is 28. So Y is square root of 28 square minus H sub C square, which is 26.309 square. So Y is 9.583 meters. Then, finally, cosine of alpha equals Y over X. So, we can now solve X. Cosine of 28.722 degrees equals Y, which is 9.583 over X. So X is 9.583 over cosine 28.722 degrees. And X is 10.93 meters. So that's it for this video. It is now very long. So I hope that you were able to follow the explanations and the solutions for these formulas here. You may review plane and spherical, you may review spherical trigonometry for particularly on the topic on the terrestrial sphere, where you can find their law of sines, which is easy to recall also, and law of cosines, or there are two laws of cosines for the sides and for the angles, but based on the formula we can also easily recall them.